Good afternoon or good evening, depending on where you're at in the world. Welcome to the second day of the 2020 International eConference on Atheism. My name is Dr. Darren Slade. I'm the president of the Global Center for Religious Research, and I want to say thank you so much for coming out and supporting us. What's fantastic about these academic conferences is that you didn't have to get out of bed. You didn't have to get out of pajamas. You certainly didn't have to buy a hotel room or an airline ticket to hear some of the latest research on the philosophical and scientific study of atheism. So thank you so much for joining us. And with that said, I have the distinct honor of being able to introduce our next guest, a man who needs no introduction, Dr. Richard Carrier, who will be presenting on Bayesian reasoning's power to challenge religion and empirically justify atheism. Now, as you probably already know, Dr. Carrier is the author of numerous books and articles, including Sense and Goodness Without God, on the historicity of Jesus, and The Scientist in the Early Roman Empire. Now, he teaches several affordable online courses in philosophy and history every month. He has a PhD in ancient history from Columbia University. He also specializes in the modern philosophy of naturalism, the origins of Christianity, and the intellectual history of Greece and Rome. If you'd like to learn more about Dr. Carrier, visit www.richardcarrier.info. And if you would like to be personally taught by Richard Carrier, you can actually go online and get some of his courses. If you go to the right side of your screen under the section that says offers, you can actually click and check out any one of his 8 courses, and you can take them at any time. So I highly recommend that you take a look at the offers section being promoted right now. Click on the link, and you can go and attend some of his courses. Now, I'd love to emphasize just one of his more recent books on the historicity of Jesus. Now, this book has made ripple effects and waves throughout the academic world. And in this book, Dr. Carrier actually challenges the assumption, the bona fide, the given that historical Jesus researchers have given that says Jesus of Nazareth was an historical figure who really lived in first century Palestine. Dr. Carrier challenges this and says instead that Jesus may have likely been a celestial being instead, somebody who was known only through private revelations and hidden messages in scriptures, and that eventually stories about the celestial being were then put into an earth setting to give an allegorical way of communicating claims the gospel and that celestial being. And then, of course, later on, these allegorical stories were taken literally. If you haven't read this book, it is incredibly influential and powerful. I highly recommend it. I would love to introduce my good friend Richard and say thank you so much for being here. The floor is yours, sir.
Yeah, thanks for having me. Well, welcome, everyone. So I've only got half an hour to do a quick explanation of what I'm going to talk about today. There is a handout. If you look at the files box on the right of your screen, you can download basically a handout that kind of summarizes some of the stuff I'll talk about today, but it also has a ton of bibliography, like useful links and articles and books and stuff that are on this subject, which is applying Bayesian logic to critical thinking in general, but more specifically today, I'm going to talk about religion and atheism. So what is Bayesian logic? Well, it began over 200 years ago. Thomas Bayes, after whom it's named, figured something out. What he figured out was that the probability of everything, no matter what you're talking about, comes down to arguing about really just 3 numbers. How likely something usually is, and how likely the evidence you have is if your explanation is true, and how likely that same evidence is if your explanation isn't true. And with those 3 questions of probability, you can actually explain all valid arguments of an empirical nature. Anything that is argued from evidence is explained this way. And that's because not only does all empirical reasoning reduce to that fact, it does so because all empirical reasoning is about a probability. It's all discussing that. And so today I'm going to quickly show you how you can use this information to critique religion and defend godless naturalism as well as the most credible explanation of everything that we know. just half an hour today. But I discuss this more extensively and take all possible questions on it beyond the half an hour Q&A we'll have after this today in several online courses that I teach. In particular, my course on critical thinking, my course on counter-apologetics, how to address religious arguments, and my course on historical methods for everyone, which is about how to reason about history. And the key thing here is that everything is a probability. When we say we know something or that some claim about the world is true, what we really always mean is we know that that thing is so very probable that we can trust that it's true. In other words, it's being false is so very improbable that it isn't reasonable to expect it to turn out to be false. So we just operate as if it's true. And every argument or question about what exists, what's true, is really an argument or question about a probability. So it's all probabilities, and probability is math, unfortunately. Some of you are scared of math. I promise the math is super easy today. I will not get into very heavy math at all. But the point is that if we're talking about a probability, if we're trying to figure out what is the probability of this claim being made, or the alternative explanation of the same evidence, that means we can turn to Thomas Bayes. We can go back to his idea and use what he learned to try and analyze these arguments and see where they might go wrong or how we can make them go right. Now, probability itself is a modern invention of specialized notation. Psychologists have found that human intuition, or brains, are inherently made to understand probability more when stated as odds. So, for example, you say 1-to-1 odds. Like it's equal chance that it's going to happen or it's not going to happen. Whenever you say 50-50 odds or 50-50 chance, you're basically saying 1-to-1 because 50 divided by 50 is 1, so it's 1-to-1. Or if it's 2-to-1 odds or 1-to-5 odds or whatever, the chance of something happening, our brains more intuitively understand it when we think in those terms. Or we can think in chances. So, for instance, there's a 1 in 3 chance it'll rain today, or a 1 in 100 chance that I'll get into a motorcycle accident, or 1 in 1,000 chance of this, or 1 in 1 million chance of that, and so on. Similar, our brain works with that more similarly, more easily than putting things in percentages. So I'm going to use the odds form today. And in fact, I'm going to teach you right now all the math that you need to know, which is not much. So what I'm going to do is I'll bring up the whiteboard. And if you go around, say 50-50, let's say you're starting your claim, you have no information that the claim is more likely true, you have no information that the claim is more likely false. As far as you know, it's as likely true as false. So you say it's 50-50 chance that what I'm saying is true or not. And that actually, you can just reduce to 1-to-1 because it's 50 over 50 is the same as 1-to-1. And then let's say you come along and you find some evidence, and the evidence is twice as likely to exist if your expectation is true. Let's say you're talking about it's going to rain tomorrow. It's 50-50. Normally, the odds in this particular season is 50-50 on any given day that it'll rain, but you get some information about some growing storm clouds or whatever. You see that when you see that, that's twice as likely to occur when it is going to rain tomorrow than when it's not. So now you have 2-to-1 odds. So you started with 1-to-1. Now you've got these clouds. They're twice as likely to exist if it's going to rain. So now you've got 1-to-1 times 2-to-1, and that's just 2-to-1, right? 1 times 2 is 2. 1 times 1 is 1. And it doesn't matter what numbers are. That's how the math works. If this was a 3 and this was a 2, it would be 3 times 2. It would be 6. And if on the bottom, same thing. So that's really it. All we're going to do is odds, and it's just simple math like that. So getting back to where I was. Now, this is the easiest way to talk about probabilities. So I will only use the odds form of Bayes' theorem in this presentation. And if you've downloaded the handout, you'll see a simple statement in there. You should think of Bayesian argument as like any other logical argument. It just follows a simple formula. Don't even think of it necessarily as math. It's just logic. And the basic state, you can restate it simply as this. The final odds that a claim is true equals the prior odds that the claim is true times the odds of the evidence on the claim being true rather than false. So there's just two statement of odds. One is what is the prior odds and what is the evidential odds. And when you multiply those together, you get the final odds, which is just basically the probability that your claim is true or false, depending on how you're organizing it. So you can simplify it to just prior odds equals evidential odds times the final odds. And that's final odds on the claims being true. The prior odds times evidential odds equals the final odds. So what are the prior odds? What do we mean by that? That's the outcome of countless previous calculations of the final odds. So probably done intuitively your whole life. You've not done this math consciously. Your brain just did it for you. And for humanity, across generations of humanity, the same thing. Prior odds are how things have turned out usually. And that's like weather reports. When you say, like, in this season, prior examples, prior evidence shows that every other day it rains. So it's 50-50 chance it's going to rain on any given day. That's a prior odds. And then when you get evidence that might change your mind about this particular day, that can change it. And that would be your evidential odds that I just gave you an example of earlier. And that just updates your prior odds, gives you the final odds it's going to rain tomorrow, or anything else, any other claim. It doesn't have to be a prediction. It can be whether the claim is true or false and so on. And that's the point of prior odds, is that it's what has usually turned out to be the case, what things usually continue turning out to be. It's based on your past experience. It's based on evidence, but it's all the past evidence of other cases. So, for instance, if when we reliably investigate a miracle claim, if when we do that, we always discover that it was a fraud or a mistaken impression or misreported or something like that, if it always turns out to have been some non-miraculous explanation, and we do this 1,000 times over the centuries and always find the same result, then we can logically say the odds against the next miracle claim being true are 1,000 to 1 against. That's an example of prior odds, and it's based on evidence. It's not made up. It's not something that we just conjured out of air. It's based on the fact that prior cases over centuries, in many, many cases, that's how it's turned out. So it's 1,000 to 1 at least against the miracle claim turning out to be a real miracle, as opposed to what it's usually turned out to be on prior examples. Now, of course, that just gives you the prior odds. What if you've got really special evidence for this one miracle? Maybe this is the one time we're going to prove that a miracle is real. Well, that you start with the prior odds and you have to multiply it by the evidential odds. How good is your evidence for this? So what are the evidential odds? That's how much more likely is the entire collection of all the available evidence that we have if the claim is true, rather than if the claim is false, or how much less likely, depending on which way the evidence goes. So, for instance, if the evidence is 10 times more likely to exist if the claim is true than if the claim is false, then our evidential odds are 10 to 1, right? It's 10 times 1. Or is it 2 times less likely? Then it would be 1 to 2. Or it could be only slightly more or less likely. It could be 99 over 100. There's lots of different ways you can state it depending on what it is. How likely is this evidence if the claim is true versus how likely is this evidence if the claim is false? And that ratio gets you your evidential odds. And this your brain is doing intuitively all the time. This is how you're always evaluating evidence. Your brain is doing this math for you. Your brain is doing the prior odds calculation. Your brain is guessing on the evidential odds, and it's sort of roughly ballparking the result for you. And that's how you reason most of the time about evidence, when you're reasoning evidentially. So that's, again, if it's 10 times more likely, evidential odds are 10 to 1. Since 10 is 10 times 1. If it's 2 times less likely, then the evidential odds are 1 to 2, since 2 is 2 times 1, and so on. Now, the prior odds are important here. You can't ignore them because we can't ignore history, right? Our conclusions about what's plausible now are based on a vast body of accumulated past evidence, and we can't ignore that evidence. And so this gets us to my first example, which is what we would call the argument to naturalism, or just the naturalism argument. And that's, I'm going to sort of roughly sketch it out. You can get much more specific and careful about it, and I do in some of the writings that are linked in the handout. But to put it simply, over thousands of years, there have been millions of claims that have been made that things in the world are caused by supernatural powers, gods, and the like. From lightning and crops growing to individual miracles, communications from gods and spirits, and so on. Magic, everything. We've had millions of these claims. And every single time any of those claims actually got reliably investigated, it turned out to be the reverse, that the cause was mindlessly natural or humanly contrived, which is also just as natural. That has happened over time and time again is what has built our prior odds heavily against the supernatural at this point. It didn't have to turn out that way. we could have found ourselves in a world like Harry Potter's or Middle Earth or any superhero universe that you want to imagine, where the supernatural is a matter of routine. You find it everywhere. The more we fail to find the supernatural in a world, the less and less likely it is that there is any in that world. And we just so happen to have found ourselves in a world where there so far hasn't ever been any. So there probably isn't any. That isn't saying there definitely isn't any. It's saying there probably isn't any. And that conclusion is based on evidence. It's based on centuries, thousands and thousands of accumulated cases of it always turning out one way and not the other. It didn't have to turn out that way. It could have turned out the other way. We could have had a lot of evidence for the supernatural by now. We just don't. Now, if someone wishes to contest that now, after all that accumulated evidence over centuries, the burden is now on them to prove some supernatural phenomenon probable. Not merely a logical possibility, we accept that. They have to prove that it's an actual appreciable probability. And that's a lot harder, because we have already met our burden showing otherwise with the entire history of science and investigation. We have a vast mountain of evidence that we're sitting on. That meets our burden. If you want to go against that vast mountain of evidence, you've got to have a pretty big mountain of evidence yourself. So that's why it's important to talk about it as probabilities rather than possibilities. The debate between the supernatural and the natural is always about what is more probable given the evidence. And that's why we call supernatural claims extraordinary claims. And you know the statement, extraordinary claims require extraordinary evidence. It's often applied to claims of the supernatural. The reason we say that supernatural claims are extraordinary is because that's how the evidence has turned out over centuries. The supernatural claims are extraordinary claims in precisely the same way and for precisely the same reason that natural explanations are not extraordinary claims, because they quite typically turn out to be true. And that's just the way it's turned out, and that evidence stacks up. It has an effect. So Bayes' theorem actually explains why we are right to be skeptical of supernatural claims now, and why science is right to assume explanations are going to turn out, yet again, to be natural. Anything we haven't explained yet, odds are it's going to be some natural explanation, because that's how it's turned out millions and millions of times before. So Bayes' theorem doesn't just do that. It also explains the logical validity of several principles we count on a lot in critical thinking. For example, I just mentioned extraordinary claims require extraordinary evidence. That's actually correct. And as we said, the very phrase extraordinary claim means a claim with extremely low prior odds. Let's say 1 in a million against. To say it's extraordinary is saying it just isn't the sort of thing that ever turns out to be true when thoroughly or reliably investigated. So let's say, again, let's say it's 1,000,000 to 1 against. Then we could say a claim that has turned out to be true no more often than 1 in a million times is extraordinary. Then extraordinary evidence means that the odds of the evidence on the claim being true rather than false must be just as large or larger. So if the evidence we have is 1,000,000 times more likely to exist if it's true than if the claim is false, then we'll get that extraordinary evidence. And I'm going to show you how that looks again in notation here. So if we have the extraordinary claim is 1 in a million against, and we would need to reverse that around, we would need evidence that is 1,000,000 times, my writing is terrible, 1,000,000 to 1. And then you multiply those together and you'll get 1,000,000 over 1,000,000, right? Which would just reduce to 1 to 1, which would get you to even odds. Even odds that the supernatural claim is actually supernatural, that it actually is true. So you actually need better evidence than this, right? You need something more than that. So let's suppose we have 1 in a million against. I'll just write 1 in a million against. And you have evidence that's 2,000,000 times more likely to exist if a claim is true. And that's some really extraordinary evidence, right? And then you would end up with 2 to 1, right? So then you would end up with 2 to 1 odds that this actual supernatural event actually occurred. So you actually can prove miracles. You just need really, really good evidence that is so improbable unless the supernatural is actually happening. And that's what we never find, right? That's in 200,000 years, 200 years, 2,000 years. We've never found an example of any evidence for a miracle that was anywhere near this good. But that's what you need. You need some extraordinary evidence like that to actually turn things around. So, and again, like I said, any evidence more than that, if it's 1,000,000 to 1 against, you need evidence that's 1,000,000 times more likely. If you get that stuff, you need more evidence than that to get it more and more probable. But any less evidence than that, if the evidence isn't that good, then you just can't get the claim to be probable at all. There's no logically valid way to get the claim to be probable other than to get this evidence that has extremely low probability of existing unless the claim is true. That's just the only way you can ever get the probability up. And this is actually what we always mean intuitively by evidence being strong or weak, or evidence at all, right? It increases the probability of a claim being true. That's what we mean by evidence. And if the evidence is strong, we're saying that it really increases the probability by a lot. If the evidence is weak, we say it's increasing the probability of the claim only a little bit. If it doesn't increase the probability of the claim at all, then it's not evidence for that claim. And so that's how we actually operate intuitively. And so what I've just done is I've popped the hood on your brain and shown you the math that your brain is doing. And now that you know that, you can actually tinker around and actually use this and correct perhaps when your brain is intuitively going wrong, or when someone else is doing so. So Bayes' theorem has given us a way to logically validate the entire concept of evidence. Strong evidence is, by definition, evidence that is very much more likely if the claim is true than if it's false. It's evidence, in other words, that's very unlikely unless the claim is true. Weak evidence is, by definition, evidence only slightly more likely if the claim is true than if it's false. And if the evidence is just as expected, whether the claim is true or false, if it's equally likely, both it being true, both being false, they both expect the exact same evidence. If the evidence is just as likely either way, then we have odds of 1 to 1, equal odds on the evidence, regardless of whether the claim is true or false. And if you did that, if you show that in a thing, let's say you have prior odds. Let's say your prior odds are 1 to 2 against, and you have evidence that's equally likely whether it's true or false. If you do that, you just end up with the same prior odds as your final odds. This evidence did nothing. It did not increase or decrease the probability of your claim. And so you need evidence that has a high value up top, right, over the value below. Your x needs to be high and your y needs to be low. This is if the probability of the evidence, if it's true, the probability of the evidence if your claim is false. And that's just the only way to do it. Logically, that's the only way to get a claim's probability up. And so, once again, any value multiplied by 1 remains unchanged. So that kind of evidence, the evidence if it's 1 to 1, it's equally likely on both possibilities of the claim being true or false. That kind of evidence is useless. And so now we know the logic behind why it's useless. That's how we know the evidence is useless. And we know what it takes now to make evidence useful, to make it actually do work, to increase the probability of a claim. So another example of a principle we often rely on that Bayes' theorem explains and validates is the argument from silence, right? So we know sometimes the absence of evidence isn't evidence of absence, but we also know sometimes it is, right? So how do you tell the difference? How do you know the difference? Well, the difference is when the missing evidence really is expected to exist, then its being missing is improbable because it's unexpected, and that's just another word for improbable. Unless the claim is false, then you fully expect there to be no evidence, right? If the claim is false, the evidence is entirely what you expect it to be, there to be no evidence of it. So this gives us a disparity in evidential odds. So if we go back in here and we see, we start with prior odds, equal chance your claim is true, 1 over 1. And you have missing evidence that you don't expect. And let's say that it's 5 times more likely that you wouldn't have that evidence if the claim is true than if it was false. Or we can do it that way. But you would end up with 5 to 1, right? So what you need is evidence. When there's absence of evidence, for absence of evidence to be evidence, you need to expect that evidence to exist. So it's if you can explain it away, for example, if you invent the idea that there were invisible ninjas that came along and destroyed the evidence, then of course your odds are 1 to 1. Now there's a reason why that doesn't work. I'll get to that in a moment. But you can at least get to the point where now we expect the evidence to not exist, whether it's true or false. It's equally likely to not exist whether the evidence is true or false because it was destroyed. And if you could prove that it was destroyed, then you would be able to say this validly. So that's when argument from silence doesn't work. When the argument from silence does work is when the evidence is missing, being missing is very unlikely. So for example, if there were only a 1 in 10 chance that the evidence we expect would be missing, that's a 10% probability, right? So it's a 10% chance that that evidence would be missing, even though the claim is true. But if the claim is false, it's 100% that we would not have that evidence. And of course, 10 over 100 is just 1 over 10, right? You reduce it. So the odds against your claim are 1 in 10, 1 to 10, actually. So if your claim started 1 to 1, and you have missing evidence that you should have, you end up with the probability of your claim being true of 1 in 10. So you've gone from 1 to 1 to 1 in 10. The probability of your claim is dropped precipitously because there's evidence missing that should be there. And there's no good explanation for why that evidence isn't there. So that's when arguments from silence work. So that's when the absence of evidence in this case really is evidence of absence. But again, if we fully expect the evidence to be missing, then it won't be, because the probability of the evidence on both being true and false is exactly the same. So it doesn't increase the probability of your claim at all, or decrease it. So now all of the same stuff, that's how we can work with the argument from silence. Use Bayes' theorem to figure out when is an argument from silence effective and when is it not. And it's all based on how expected is the evidence to be missing. If your claim is true versus how expected is that result if the claim is false. Now, all the same goes for Occam's razor. You know, Occam's razor is really popular. That is more or less the idea that the most likely explanation of something is the explanation that requires the fewest made-up things to work, to get it to work. Like when Newton explained the motions of the planets with a single force, gravity. Adding the additional supposition that angels are also pushing the planets along violates Occam's razor. And the point here is it's not that it's simpler to eliminate the angels. The point is that there's no evidence for the angels, and you don't need them to explain the motion. So let's turn around and take all of this stuff up and apply it to some arguments for God. So let me get rid of this. Actually, I'm going to put this in. So let's say we're talking about probability that God exists. Now, really, we start out with very low probability.